move from this kind of data, operational data, and Toyota and Sony insurance company are using automobile probes. And NTT Docomo Healthcare, there's a financial work done by Hitachi, and many people are trying to use this mobile data because we expect, the huge amount of data coming in a mobile network. So, well, our team at University of Tokyo tried to understand what kind of data that we can use in mobile network. And the first category is about traffic data, and this is per packet traffic trace. And although it's very useful, but sometimes there's a privacy issue, and this is especially interesting for advanced security like attack detection and prevention. It's hard to use this one if it comes to a privacy concern. And application content data, I think as you know, the Facebook's news and social network search content is getting used, and again, this has been pointed out to have like privacy issues. So we have to be a little bit careful using this data. And the third one is an interesting data, operational data, because the network equipment is being softwarized. Many people are using a software program to develop the network equipment. So we can insert a data footprint easily and flexibly so that we can detect anomaly and predict the malfunctions. But as I said, we have to be a little bit careful about privacy issues. GDPR and the constitutions of Japan prohibit looking inside the packet payload. And of course, there's a network neutrality discussions happening in the US. So I don't have to teach what the GDPR means, but it says that privacy must be respected. But at the same time, so this is an interesting article, that predicts that 2017, published in 2017, Gartner say that they predict that by year 2019, that's next year, the 50% of citizens are willing to give out their personal data for, sharing the personal data for, drawing the interesting conclusion. So having seen all these, we think that we should be prepared for, this coming age. And what this workshop is about, the next generation network topic. So the mobile data, we like to understand this problem. So, and there are very interesting trends in infrastructure these days, three of things. And I have to, I want to spend a little bit of time for each. And softwareization, the data plane innovation is happening. So there's a barefoot, produced and MP4 programmable network. And we have been doing this data plane innovations using our, programmable node called Flare. As maybe Ray know that. And unlicensed band mobile networks and also in-network machine learning. That these are the three interesting trends that is happening around infrastructure. So let me first talk about softwareization. So what do we do about softwareization? So everything is getting this softwarization everywhere. That means that from sensors to IoT gateways, and the EPC and the mobile edge computing is attached. And of course, we have a cloud data center. Lots of software programs running to host the services, web services. All of these components are not softwarized so that we can do data analytics, end to end everywhere along the data path. So especially, we are interested now to look at this place, to be an EPC and MEC, because softwareization of disease, hasn't been explored fully yet. So we take this, so base station equipment, and usually this is a hardware, but now people are doing a software development software version of E-B. But conventional approach is that we use CPU for upper layer and DSP and FPGA. We use that PHY and MAC because we have to have fast processing. But because of Intel and AMD developing this very high frequency core processors, we can use the CPU, just CPU, to do E-B processing. And also EPC can coexist. For pilot core software can coexist. And also mobile edge computing services also coexist on the same hardware. So we can share the hardware resources among E-B, EPC, and MEC. And then we can do interesting data analytics that is possible. So the challenges here is that the processing power for complex data processing, because we are doing interesting things here, but you have to consider how we use this processing power for complex data processing. And also stable operations, especially preventing fluctuation in latency, because if you use software, so then you have to be careful about latency fluctuation, because people don't want to have jitter in the data path. This is especially interesting to us because lots of virtualization is happening, and sharing computational resources with network virtualization, function virtualization is an interesting challenge here. Okay, so let me briefly show our the movie of our software-based base station. Well, sorry about the slide, but this is taken from open air interface, open source, and we worked React, and we made it very stable. And it says LTE, 4G network, but it's connected to our, base station here. It has an antenna, and we are using experimental LTE license band at 1.7 gigahertz. This is FD LTE. And here, so we have Intel servers, two 1U servers, and here's an radio equipment and antenna. So we mostly work, ran this software to do this LTE base station. But now, you can insert the data collection point in this software so that we can do data analytics. So the breakdown of our software is like this. We have a radio box here, but it's attached to the Intel server. And Intel server is running a LTE soft modem from PHY to, up to the coding and decoding stuff. Some people use FPGA to offload FFT and IFFT. Now, GPU is getting used for this FFT processing, but purely using, just using the CPU, you can do this kind of processing now. And EPC, many people have already done a virtual EPC. So altogether, this part is running on top of Intel or AMD CPUs, and we just attach a radio box, which is produced by some company, and we are using USB board attached. Okay. So the challenge of software is software file layer. So there are two challenges. The primary challenge in software is how to process each subframe within only time, like a 4 millisecond, less than 4 millisecond, because we have to acknowledge back to the radio in that short time. The another challenge is that we have to reduce the cost of software computation, and there many core processors, high frequency with many core processors are helping. The cost effective is fine, and we are using AMD chip. So performance-wise, if you look at this number at the 20 megahertz, so you can do like downlink almost like about 7 megabps, and uplink is about 14 megabps, which is for commercial usage. And so we are using the commercial phones from Fujitsu. This is regular phone getting connected to this software base station at 1.7 gigahertz. And we're doing this experiment. So this is done by collaboration with the Fujitsu. So we prepare 10 UEs, getting hooked to the software-based B, and we are running, we are doing a long-running test and video streaming and voice calls on and off. This goes on over 24 hours, more than, longer than 24 hours, and it's not breaking. It's pretty stable. Now we are trying to increase the number of UEs getting connected to this one, and we are doing this experiment on campus, so which is very exciting project because, again, as I said, we can hook the lots of data points there. So, well, just for fun, so I have a collaboration with Berlin Fraunhofer Lab. So we have an end-to-end UE to UE experiment. So purely, both sides have softwareized mobile network systems, and we can connect commercial phones. Well, I didn't this person beyond that I'm showing this video to you. Maybe I have to tell them now and later. But so we're pretty happy about this experiment because we proved that over the ocean, over the continent, we can run software stably. So the power of software is something probably we can use that for commercial service as well. So lastly, we're doing this collecting operation data in real time. So we are still investigating this data. But the important thing is that we insert arbitrary 40 hook points in the software so that we can real-time monitor all the parameters that we can take from this software-based station. So if you don't, we can't draw the high-level conclusion from the current set of parameters. So then you can choose to, have a different set of parameters, and then you can do some sort of machine learning technique to draw the interesting conclusion here. Okay. So let me talk a little bit about the unlicensed frequency band for mobile networking. So in Japan, I think this is Japan only frequency band, but it's called SXGP, 739 over LTE frequency band. So we used to have this codeless phone at this bandwidth. Frequency band, and it's 1.9 gigahertz band. But now, codeless phone is getting obsolete. So we, some of the group in Japan thought that maybe we should make it compatible with LTE. So now we have an unlicensed LTE band, which can be used for M2M and IoT solutions. Okay, and we took, this piece. And what we did is that combining with our software-based station, we connect smartphones, IoT devices, and at band 39, and we have a bunch of these radio equipment. And so here, we are not using software yet, but we can collect the traffic data, operational data, and we create a repository, real-time repository, and hire graduate students to use these smartphones and IoT devices. So real time, we are getting data. So the point here is that the non-operators like us, like a university people, can perform data analytics on the real traffic, operational, social mobile data freely. So, well, if you have unlicensed band, I think in the US, Qualcomm is pushing this multi-wire unlicensed band, which is very exciting for us for mobile data analytics. So the last bullet in network machine learning. So we have lots of machine learning inside network research here. So the data plane innovations, I think many people would know P4, and we think that it's a powerful tools for machine learning. So the important point is that flexible infrastructure is getting ready for for us to use, so we can sense, analyze, learn traffic in the data lane. So we can enable data analytics. And for the summer, we are trying to do this advanced traffic classification without violating privacy, because we have to respect the GDPR kind of stuff. So it's a marriage between data plane programmability and in-network machine learning. So as a startup, as I said, we try to attack this very basic question. So what kind of application is transmitting given flow? So ISPs are pretty interested in application-specific traffic breakdown. So usually what people get is that total traffic change over time, but sometimes their backbone is getting pressed by very high volume of traffic, but they don't know why. For example, your smartphone's operating system is getting upgraded, at the same time, and it's pressing their backbone network. So ideally, what we would want to do is that not just the total traffic, but per application traffic is shown here, like tethering Facebook or YouTube. We have to know the application-specific traffic breakdown here. So can we do this using our programmable data plane equipment? So that's the basic question that we asked, and we have been working for several years now. And this is done in MVNO. We have lots of MVNOs in Japan. So between the MNO, mobile network operator, and the cloud, we have a mobile virtual network operator here. So we add mobile network virtual network operator to put our node. One is Flare. We try IP4 as well. So the idea here is that as soon as these phones transmit something, we modify this the smartphone's operating system so that it attaches some extra information to the packet. So it's a meta information like application name that is transmitting a given flow, and we monitor this telemetry. We monitor the traffic, and we associate these characteristics with the application name and bring it to the cloud so that we can use GPU to do a deep learning. And once we learn, there's a feature data, so we update a classifier here, and we do a traffic classification based on the application. So the regular phones are transmitting the packet, which is not tagged, but it's because of this machine learned the traffic classification, it goes to different slices. So application 1, 2, application N, and we can do mobile edge computing for particular applications. So I'm showing the video of this supervising smartphones, how we generate this traffic for deep learning, which is a bit interesting. We modified these smartphones, and we put this Flare node programmable node in an MVNO. This is a remote console, so you can check what it is trying to do. So I'm operating these smartphones, and this is Chrome software. So then it detects Chrome is transmitting packet. So I'm operating Firefox, and it's detecting the Firefox. So this part is 100% accurate because I'm attaching the meta information to, in fact, we're using a TCP SIM packet trailer, and we have many bytes there. So but it goes on and goes on. As long as the application has a process name, it gets shipped at the trailer or the TCP SIM packet, and it's going to be detected at a programmable node. And using this 100% accurate information, we put that to machine learning, and we do deep machine learning to. We also record the characteristics of the traffic and match up, this information. So again, I'm showing this part. I'm generating a supervising smartphones. We attach application tag and instruct this deep learning machine engine and updating the classifier so that we can apply this classification engine to the regular smartphones traffic. So we use a TensorFlow deep neural network open source software, and we are taking the usual 5 tuples and also with additional features without violating privacy. So many people here may think that I'm doing a DPI, deep packet inspection, but we are not doing deep packet inspection. But instead, we are using some additional features which are not violating our privacy. Okay. I'm showing what kind of features that we are using. So just to show the result of our experiment. So traffic, we take 39 days of mobile phone traffic. My graduate students are happily using the free phones and generating this traffic. And the target is 200 applications. Taking the 200 applications and from the characteristics of the traffic, can we guess what kind of application it is for a given flow? So as I said, we use usual 5 tuples with additional features, and DNN, we use 8 layers, and this is the graph of the accuracy. So if this is the number of days of the traffic that we use for machine learning, and the more data you use, this accuracy curve changes. 1 is the max. The accuracy 1 is the 1.0 is the max, and as you can see, on average we can achieve like 93.5% of accuracy. Taken from traffic, and then you guess application, and 93.5% of the time you can guess the correct application. But from this, well, by the way, the yellow curve is accuracy, and the blue one is a traffic volume per day, normalized to 1.0 maximum. So as you can see, so this accuracy changes over time, but if you use more and more data, the accuracy kind of decreasing a bit. So this means that you have to do this in real time, because the data, characteristics changes very rapidly, because people are using different application day by day. So ideally, we have to use the real-time supervising data and instruct the machine learning engine so that we can use the latest real-time data to do machine learning. Okay. And we noticed a very interesting thing, the TTL, counterintuitively, because we didn't expect this, the TTL is most contributing to the application identification. So, for example, so this is a test accuracy. If we use a feature vector of the server IP server port and buckle, and if we add a TTL downlink and uplink, so then we can increase accuracy by 20%. Okay. So I wonder why the TTL is contributing most. And then this is a mobile network from the PGate to the server, which is very high association between the service type application and TTL. Number of hops changes per application. But until we do this machine learning, we didn't expect that the TTL is most contributing. That's an interesting result. And again, the packet size, we try to do a packet size changes over time. We take a series of packet size of the first 5 packets of each direction for a given flow, and then we can increase the accuracy by 10%. Okay. So we don't know the reason why it was as a very good result, but in total, so we can achieve like over 90% of accuracy. All right. So I have talked about many infrastructure stuff, but let me switch gear a bit and talk about a use case. People might think that this has nothing to do with the stuff that we have been talking about, but just enjoy this application, and later I come back to the problem of the stuff that I talked about. So we are doing a 4K and 8K real natural surveillance using the 5G cellular. As I said, I'm doing the 5G stuff. So this is the widest KPI of the 5G mobile network, and as you may know, we can achieve like over 10 G bandwidth, and this kind of application is called enhanced mobile broadband (EMBB). And people have been discussing, what can we use this high bandwidth for? What kind of application is possible? And KDDI and I try to think of this application. We have drone, and here's a 5G tablet, the real 5G tablet by Samsung, and we use millimeter wave, 28 gigahertz band, and you can drive, you can fly drone about 150 meter above the ground, which is a low, constraint at a low range band. But you can shoot 4K video feed, and then you bring this video feed real time using 5G to the ground, and you can watch the 4K movie in real time. So we can achieve for this particular application, we can use a 200 mega BPS. But when we tried that, we found many things. Okay, so I'm showing the how we did this experiment. On campus, we fly this gigantic drone, and the president of my school is not very happy about that because it's pretty dangerous looking. And this is a radio equipment, and unusually, so it's facing upwards because we have to capture the signal from above the ground in the air. The drone is transmitting signal to this equipment. And this is the feed shot in the air. So these are the KDDI people and waving hands. And this is the real 4K video feed. We are stitching 6 fish eye lens cameras feed together. So there's some delay. And you can move around. If you have a VR goggle, so you feel like you are in this drone flying around, which is pretty cool demonstration, and my students love this demonstration. So, well, this is good for a high bandwidth, but another interesting API of the 5G mobile is ultra reliable and low latency communication. We can reduce the widest part of latency below 1 millisecond. So that's the goal. Okay, it's called URLC. Okay, so we thought about how can we use this feature of coming the 5G mobile network. So what we did is that we thought about object recognition. So we take this open source software, which is called YOLO. I think you might be familiar with that. This is the 30 layers of a deep neural network, and taking real-time webcam video feed and analyze this data, which is pretty fast. And we want to use that in a drone and try to detect object in a short time and send it to the ground in a very short latency. And because we have to load in this equipment, so we are using small form factor GPU. NVIDIA is giving this Jetson TX2, which is very small, like name card size. But we ported this open source software of object recognition, and we run it. So we are actually running in my office, which is pretty, good looking. It's detecting laptop. Sometimes it makes a mistake. I'm trying to deceive this, machine, and wearing the same cut tie with the shirt, but it's not deceived. It's detecting a tie. I take out a cell phone and try to make it look like a mouse. And for a short time, it recognizes a mouse, but then it realizes that it's a cell phone. So, well, this is a 2 or 3 frames per sec because it's a very small GPU. So you can do, okay job for object recognition, but it's not enough for the real-time use. And we look at this, GPU on the drone and try to capture the person on the ground, and it's detecting most of the time. And as you can see, well, it's very small. I'm sorry, if you don't see these numbers, but it's 15 to 20 frames per sec. So if it is a 20 frames per sec, so that means that the 50 milliseconds per frame. So 50 milliseconds, we can recognize the object and send it to the ground within several milliseconds, which is a viable application, we think. Okay. And another video feed, I asked KDDI people to be on the ground. This is a very hot weather, and they don't like to be on the field. But I asked them, and 5 persons are detected successfully. And we are using this very simple model for detecting objects. So it's fast. It can go to like a 15 to 20 frames per second. But if you have a complex object recognition, so then the frame rate is decreasing. Okay. And my student took, this is a random video from YouTube, and I tried to apply the same model. Mostly it can detect the object of the fine, but sometimes it fails to detect, like cars here are not detected there, and there's a big square called car, which is wrong. So we learned that we have to train the model precisely, tailored for this environment that you are using. This is taken from the Stanford data, and we did the same thing. Mostly it's working correctly, but well, for our use case, we have to train this machine learning engine more to get the accurate object recognition. So now you might ask, why does this John app have anything to do with softwareization and the data analytics? I'm coming back to this problem. Okay, so I said EMBB, URLC, these are the 2 major characteristics that we are looking into. But we put these 2 applications together in a drone. Suddenly, it's seeing the problem, because we are sending a huge traffic over wireless link over to the cloud, and at the same time, you have a very short latency traffic going across, right? So if you if you transmit two very different traffic over a single link, so then you start seeing the problem, because this is getting late because of this high volume of the traffic. So you have to do something here. The first thing you have to do is, based on the application kind, you have to classify. So there, we can do machine learning technique to the application-based traffic classification. And then after classifying the traffic, we have to do application-based, slicing, OS. Okay. So we sort of create a URLC slice and an image slice. Okay. So, and also we could do network-aided object recognition too. I can talk a little bit about this later. Okay. First, run slicing. After detecting the application kind, so can we do, application-based QoS or not? So this is still a baby step, but we modify this softwareized Node-B. We have a luxury to modify the resource block scheduler, how many blocks that can be assigned to each application. And we change the scheduler so that it can, UE2 application can get the higher bandwidth than the UE1. So we can do this kind of fancy resource block scheduling for app-based system. And we are spending more and more time in this problem, because it is very important for a 5G mobile network. And eNode-B is not enough. So there's a component called EPC, and we are looking into this low latency slice. What can we do by changing this scheduler? And this is classic US problem, but we are treating this as application. You have to have a very low latency end to end for this particular application. So we have to modify this scheduler for EPC. So this is a quick summary of the result. Our paper just got in IEEE CloudNet and presenting this. But without a slice, without competing slice, we can achieve like a 5 millisecond to 10 millisecond end to end. This is x-axis latency and y-axis is CDF. So without a slice, competing slice, we can achieve 5 to 10 millisecond, right? And if you want to do QoS, many people might think about hierarchical token bucket scheduler, which is not good because 10 to like 20 millisecond delay. So we don't like that. So we changed this, QoS scheduler to the hierarchical fair service curve. I don't have time to go into the detail. If you later, I can explain, what we do. But this gives us a best isolation because it gets close to non-competing, no-sharing performance here. Okay, one more thing. Okay, I'm getting to the end of my talk. So about the object recognition, can we do something smart in network, inside a network? So we're working on a network-aided object recognition. Okay, so the problem here is that we have a small GPU, and which produces low the frame per sec, and so because of this problem, many people, conventional approaches is that they don't do GPU here. They bring the GPU in the cloud and they do object recognition here. But this method has a serious problem because you have to send 4K video feed over wireless and also transport to get to the cloud, edge cloud, to do object recognition. So just one application case is fine, but if you want to have many instances of this kind of application, so this high bandwidth part is getting in the way. So we want to reduce this bandwidth but achieve fine object recognition. So what do we do? Our proposal is split and compress DNN. So the idea is that if you look closely into this DNN layer, so there are at some point, so it has 8 layers, but at some point, layer doesn't produce much data. So we split this DNN and move first part to drone, and the other part stays in cloud, so that we can have a low bandwidth. Okay, so this is a splitting approach. And if you can afford more computation, so then we can add more deep learning, network layers, so that we can do even lower bandwidth here. Okay. So if you compare, well, here we have a data plane innovations because we are doing a network processing along the data path, and if you can do that kind of thing, so we can have this, application scalable. So this is, just we got this result, traffic reduction by this idea. So if you do a cloud only, we can get a 2 megabyte per frame, so which is very high bandwidth. But if you split at the right point in a DNN data model, so then you can reduce the traffic significantly. And if you can afford a little bit more computation, we add a compression DNN, and we can reduce the throughput by 84%, but we lose only like 3% of accuracy in object recognition. So again, this is still a big step, and we can, we try to use network data plane programmability to kind of helping this, particular application, which is very exciting. So I'm running out of time, so let me summarize my talk. So what I wanted to tell you today, this is a major takeaway. So we noticed that there are mobile network traffic increasing, and but there are important 3 trends in infrastructure to facilitate this mobile data analytics. So the first one, softwareization. The complex data processing is enabled by using a deeply programmable software infrastructure, and the unlicensed band, non-operated can do this data analytics. I'm sorry if you are operators, but we are not operators, but we can afford to do that if you can use unlicensed band. And in network machine learning, many people are doing that, but data plane innovations are aiding this particular very interesting topic. Okay. Well, this is the end of my talk. I'm happy to take any questions. Thank you very much.
So you talked about a lot of softwareization and how useful it is. So I'm wondering, in the networks, what cannot be softwareized, but right? So I want to find the boundary here. So part, I know the function can be something can be softwareized, but which part is not? So that's my first question. Second one is that in the beginning you said variation in latency is important, but when we run software, because depends on the scheduling, multiple things. So in general, that kind of like time span in software is unpredictable. So do you have anything to share with us? Thank you.
So thanks for good questions. So the first of all, which part cannot be a software? I think a lot of things cannot be a software, but my point in a softwareization is that, everything has to be, I'm not saying everything has to be software, but it's a flexibility and a performance trade-off. So if you have a fairly flexible hardware, so that even a graduate student can program this, data processing, which is fine. So I'm in fact not interested in which is not softwareized and which is softwareized. But to answer your question quickly, so in this particular B case, so we have pretty solid software here run, and except for radio is not softwareized per se. But if we push this softwareization using Intel hardware, we may be able to solve this problem. But if we can't, maybe you can use like a FPGA attached to the CPU, because Intel has this Xeon with a FPGA. So the point is that we have to be able to bring innovations, for example, inserting a data point. But in order to do that, we need a fairly flexible hardware or pure software approach on top of a general purpose processor. So that's the answer to your first question. And what was the second question? Okay. Variation in latency. I said, the boundary time. So far, as you can see in my bandwidth, number here, so we can achieve like a 4 millisecond delay bound here, so which is fine in this case. But I think in general, you are right in that we have latency, unpredictable latency in pure software. So maybe we may be able to solve this problem by doing active queuing, or maybe we have to use particular hardware acceleration for that part. But again, getting back to your first question, my point is that always flexibility and performance trade-off. We can use the right equipment to achieve your goal.
Thank you, Nakao-san, being talk. So, in general, I think you are trying to make the case for enhancing or empowering the data plane to do more useful functionality. So, I'd like to maybe try to disentangle the different aspects that I saw in your talk. So, I think in the first part, you talked about enabling, for example, mobile operators to classify application traffic with machine learning and so on. So this is something that you can do basically without touching the protocols. You can just look at 5 people or what you use. And the second part, where you about, for example, splitting up the DNN between, say, a mobile device and a cloud device. So in my view, this is a slightly different, say, layer you are working on. This is perhaps more the application layer, where it's not sufficient, to just do something with unmodified protocols. For that, you would probably need a different kind of protocol architecture, maybe something like edge computing or in-network computing. Would you agree to that?
this is what I like most about SIGCOMM. Thanks for a very good question. So to answer your question, so I show, the, application of data plane innovations, which is underlying layer of like application identification and up to like a mobile, drone applications. But my point is that so now we have to think carefully that once you can program data planes, we can think about application, driven by application use case. We rethink what's the infrastructure should look like. So although I showed two different applications, underlining my, my interest is that, rethink what the infrastructure should be like. So the first application identification, we modified the protocol, but we embed some programmable component in the network to detect that application. So we are bridging between the application and network infrastructure so that operation of the network is kind of easier for operators. Well, that's the case that I want to make. If you see this, example, people might think that, okay, we abstract the network, we separate application from the infrastructure by socket interface, but you might want to bring some application context into the network so that you can control the application traffic is, in a big way. So I'm trying to pose this question. So this is a data plane innovations job to do that.
Thanks for the talk. It's very interesting. I have a questions. In part of your talk, you basically said that you have to use DNN, right? I mean, I just wonder. I know a lot of people using DNN right now, but why can't you use some other machine learning techniques? I think in terms of computation, probably is better. In terms of fundamental understanding, is probably better. I mean, DNN seems like we're doing well for images on classifications. But the thing is, when you do that, like at the end of the day, you say, oh, why packet size, why the TTL makes sense. And I think it just go back to the application domains, right? So why you abandoned other, as far as I'm concerned, equally powerful machine learning algorithms?
So thanks again for a good question. So I'm not into DNN only for this machine learning type of data processing. So in fact, in the paper, we tried a random forest and compared the performance and computation between these two models, and we tried to do more and more different type of machine learning. But because my students like to do a DNN, so we try DNN, and for random forest, it's a historical method for machine learning, right? So yeah. So, but my point is that we just showed extreme usage of the machine learning equipment like GPU, so that people pay attention to it. But as you're right, we can use any kind of machine learning technique. If in particular this case of application identification, random forest gives us a better result, so we should be using this one. I'm not tied into DNN only.
So thanks again for your very nice talk, and there seems to be a lot of interest. Please follow up individually. We need to get on with the program, so I'll ask Kiran if you want to get this session started, or who's okay. Okay, so thanks to the speaker. all set. Okay, good. So we'll start now the first session, which is called Emerging Networking Methods and Solutions. We have two papers there. The first paper is on bridging ICN deployment gap with IPoC and IP-over-ICN type of solution. So Susmit will be speaking. Susmit, yeah, will be speaking. Shannigrahi, he was with University of Colorado State University, yeah, and will be giving the talk. So I'm not going to do detailed bios, so please go ahead and stick to about 20 minutes.
Thank you. So this is a work that we did CableLabs. This is fine. Thanks. So since we are talking about software routers and software node Bs, the one thing that's great about software stack is that it's really flexible. So why stick to existing technologies and not expand it to future technologies? So this work is about bringing ICN benefits to 5G networks. So we found that ICN has a few very nice properties that can help with mobility. For example, it has stateful forwarding, so you don't need to create paths before you forward. There are caching, in-network processing, in-network data analytics. So we have all these nice properties in ICN, but how do we get them into current 5G paradigm? So one way would be to run two parallel networks, one running IP, another running ICN, and it's a bit of a cost problem, and also how do we make sure they're interoperating correctly? We could also do ICN over IP as where IP is an underlay, but then we don't get most of the ICN benefits. So there have been studies that tried to do ICN deployments. So there are three major approaches: ICN as an overlay, and then dual stack where IP and ICN coexist, and then ICN as an underlay where ICN carries the existing traffic. There are pros and cons for all these approaches, but for this study, we use ICN as an underlay. So we found that there is no additional delay for this approach, and then it's ICN only, so you keep all the ICN benefits for existing IP applications. So the primary goals for this study was to create a sort of tunneling protocol on top of ICN that can carry all existing IP traffic. So we have millions of applications that runs on mobile devices, and rewriting all of those would be very difficult. So something that can take all the IP protocols and carry them over ICN networks would be nice to have. In addition, we also wanted to have something that could eventually act as the replacement protocol for APC in 5G networks. So a very high-level overview of the protocol is we have the IPoC client, which happens to reside on the mobile devices. And then there can be several types of access points. Could be Wi-Fi, could be small cell, macro cell, doesn't matter. And then there would be a gateway at the edge of the mobile network, which will connect to the IP network on the other side. So going into a little bit more detail. So we have our existing application on the mobile device here, and then the IPoC client resides between the NDN layer and the IP layer and translates between these two. And then there is the physical layer, the link layer, that works as it does today. On the other end, at the edge of the network, we have the IPoC gateway that similarly translates between IP and NDN traffic, but it's inverse of the stack, where it receives NDN packets and then translates them into IP packets and then forwards them into existing IP network. So it also supports the consumer mobility. So the way we, the high level, at a very high level, we encapsulate the, so ICN has two types of packets. One is interest and other is data. So we encapsulate the outgoing messages. So the upstream messages are encoded in the interest payloads, and the data that's coming back that are encoded in the embedded in the content objects. So here is an example of how the actual routing works. So for example, say your mobile device has 11.0.0 something IP address. So the gateway here, it announces a name prefix, which happens to be IPoC, and then hex encoded IP address into the NDN network. And then to the internet, it announces 11/24 as normal. So when traffic is coming back, it sees that it needs to forward the traffic to 11/24. When it gets to the gateway knows that 11/24 translates to this NDN prefix, and then it forwards that over NDN network to the mobile client, which then again knows that anything. So the IPoC client translates from NDN to IPA and then forwards that up to the application stack. Okay, so a little bit details on how the packet flows work. This is IP upstream packet flow. So we have the application stack that has as an IP packet source and destination address. It comes to the IPoC client. It gets encapsulated as an interest payload. Then, so we have the IPoC, we have the NDN name, the payload, and in the payload there could be multiple IP packets. Once it reaches the gateway, the payload is separated from the name. The name is preserved in a client interest pool, and the payload is forwarded as a normal IP packet because that's what that payload is. Similarly, when data comes back, we remember the names that we saved from the outbound path. We take the first name in the list and then encapsulate the incoming data with that name and then send it back into the NDN network. At the IPoC client, the data is decapsulated and then send it up the normal IP stack on the mobile device. Okay, so the naming convention for IPoC is simple. We have the /IPoC prefix at the beginning, and then hex encoded IP address, and then a unique sequence in base 64. the names for NDN routing, those names should be sufficient. In case the carrier is using carrier-grade NAT, it could be extended to have the zone ID and then the private prefix. And IPoC could work in both of these cases. So another question is, how do we manage in-flight count and flow balance when we are sending packets out? So we keep interest deficit report, IDR. So every time a interest goes out, we reduce the deficit count, and then when data comes back, we increase it again. So that way the client knows there is if the deficit count is negative, it knows that it needs to send more interest. If it's positive, it knows that it needs to back off. So right now it's kind of simplistic, but it could be dynamically adjusted based on the traffic pattern if required. So how does this perform in real world scenarios? So for evaluating this, we used NDN-SIM. We created a very simplistic topology. We have a bottleneck link here, which is 100 megabits per second, and then we have 40 gig uplinks all the way through the producer. So the right-hand side shows the overhead IP, the comparison of overhead between IPoC and IP. So the IPoC good port is a little bit less than pure IP, about 5%, which is expected because of all the signing overhead and the name component. And the name component overhead that goes into an interest and data packet. On the left-hand side, we compare IPoC efficiency, which is the overhead for each packet. We consider IP doesn't have any overhead, and IPoC has a little bit of overhead because of the signing and the names. And this is the comparison between GTP tunneling and IPoC. So GTP has a little bit of more overhead over IP because it's again a UDP tunnel protocol, and IPoC has the ICN overhead, but it's not it's not too much different from what we see today in GTP. Okay, so the latency for single file download, we remember in the architecture we have a table which maintains the flow balance. So at the gateway, if there is no pending interest, the incoming data packets are going to wait until there is something at the gateway. So this is where these spikes are. This is what the spikes are for, because at the beginning of the flow setup, the packets are going out, and then till that table is full, it cannot send data back. So it's waiting a little bit of time before it can send data back. So that's why the increased latency over there. Once the table is full, it doesn't change too much, and it has pretty much steady latency. Okay, so the takeaway from these slides is that IPoC can maintain the current level of performance with a slight overhead. Now talk about how ICN can benefit. So we showed that it works. The performance is similar to what we see today, but what new benefits can it bring to 5G networks? So this is a handover, well, simplified handover protocol on the right-hand side. So right now, what happens is something moves. So the EV moves from one node B to another, and then there's a X2 channel that's set up so that the existing communication can continue without breaking maybe the TCP sessions. So upstream traffic goes through the target in node B, but the downstream traffic goes a longer path that flows through the source in node B, and then once the path setup is complete, then the traffic can move through the target in node B. So with ICN, that becomes a lot more easier. So we are going to talk about two modes of handover, the hard handover and the soft handover. In the hard handover, you tear down the underlying radio channel before you move to another node B. And in soft handover, you simultaneously use both, which is difficult to do today because IP uses only one route. So with ICN, this is what's. So let's say this is the existing packet flow. It goes to the router, and then the incoming packet is cast at the IPoC gateway. Now, the node B, as UE moves from one node B to another, the IP packets, as it is cast here, you don't need to go through the source in node B. You can simply transmit that interest and get the cast data back. One caveat on this is, unless you have enough caching capacity at the gateway, it's going to lose packets and then going to delay the communication. So I'm going to skip this one. The idea is the LTE handover versus the IPoC handover. In IPoC is much simpler because you don't need to go through all the overhead of setting up channels, rerouting traffic, and then continue existing communication. You can simply move to another node B and start forwarding packet on that path. The experimental setups, we had the similar bottleneck links here, but two node Bs that we used simultaneously for communication over NDN. For hard handover, with IP, you see there's a drop here, but with NDN, there's no increased delay because there is no X2 channel setup and one path. And another thing is NDN or ICN can use multiple links simultaneously, unlike IP. So here we have single link throughput, which is about 85 Mbps, and using dual links, we can utilize both simultaneously, effectively doubling the effective throughput of the mobile application. So to sum up, in this one we proposed IPoC, IP-over-ICN tunneling protocol. We found that our protocol has very little overhead and works for all IE applications without any changes. It can also bring ICN benefits to existing applications, especially for 5G networks. So we have, the code is open source. It's available on GitHub. And I think that's all I had, and I'll take any questions you might have.
In your gateway design, you make an assumption that when you issue an interest, the response coming back has to be in order?
No. So we have packet recipients both at the gateway and the client. So any out of order packet would be resequenced.
I was wondering, do you have any sort of feeling about how transport reacts to this new situation, since packet losses will be hidden if they happen on the, let's say, IP part of the Turk, and how timeouts and etc. are handled at the transmitter? Thank you.
So right now the timeouts are fixed, but it can be dynamically changed. We didn't do this for the simulation, but there is a, so the throughput would depend on the timeout value. So if you have very small timeouts, and then if the gateway here says that it doesn't wait for the packet to come in and declares that it has timed out, eventually that propagates to the client, and then the client, because of TCP, it retries, or if it's UDP, then it does something at the application layer. And if it's too large, if the sequencer is the sequencing timeout is too large here, then it waits. If there is something lost on the network, it waits for too long before it declares, it finds that there has been a packet loss. So depending on how you set the resequencer timeout here, there's a chance that your application throughput would suffer. So you have to set that a bit carefully.
So I had two questions. So one is like I thought that design was that IP was sitting on top of NDN. You actually implemented a consumer and producer IP applications to basically send and get the data between it. But it doesn't seem to be the case. You're sending one interest packet with multiple IP payloads from the client to the IPoC gateway. So in that case, how do you do the recovery? Right, so there was a previous slide, I think the previous slide in the upstream. Yeah. So you're sending IP interest and you're sending an IP packet, IP payload in the interest packet, right? I mean, I was thinking that for basically if the IPoC gateway has to get a packet from the IP client, it has to first send an interest and get the data back. Right, then there is an interest data association if you want to recover anything. But just pushing IP packets in the interest, then that association is broken and then recovery becomes difficult. Okay. Okay. The other question I had is like, I mean, you still have to handle the producer mobility too, if you have multiple NDN hops, right? So I don't think you touch that part. Yeah.
Okay, so our next paper is called Data-Driven Approaches to Edge Caching. That's good. So our next speaker is Yong Liu from NYU, and we'll be talking data-driven approaches to edge caching. Okay. And you have 20 minutes.
Okay. So, thank you. So this is a joint work between NYU Professor Chow from NYIT and also several kind of collaborators from Huawei. Of course, as always, most of the work are done by students. So, so this is outline. I'm going to give you some motivation. Then I'm going to talk a little bit about how we can predict the content interest in the context of caching for users and groups. Then I'm going to talk about our proposed hybrid edge solutions. Then I will talk about some evaluation results using a real VOD physics. Conclude the talk with some future work. So edge caching is actually promising because nowadays new content you always want more pixels. We just saw some kind of 4K zones, and now people are talking about even 24K. Try to make it even higher, a super requirement for the network. And meanwhile, also lots of content require low latency because there are a lot of kind of live broadcasts of user-generated content. Some users play games, and people are talking about VR, AR applications. So they actually require both high throughput and low latency. So, so this is why for content delivery is getting more and more challenging. One kind of a promising solution is to edge caching. So the idea is kind of intuitive and makes sense. So you try to push content closer and closer to users, right? So you're going to deploy a large number of small cache boxes very close to users. For example, you can put one cache box at the let's say base station and 4G or 5G, and hopefully you can achieve higher throughput. You can reduce the latency of content access. Okay. But there's some kind of challenges for you to do this kind of edge caching. And so one problem is since we are now going to push the cache box closer to users, each cache box only have a very limited resource availability. Right? So you cannot have the same amount of storage or memory computation resources as more centralized cache servers, which means each cache box now is not as strong as before. Another problem here is that each cache box now only handle a small number of users, right? Think about all users connected to the same base station. So we're talking about maybe hundreds, thousands of users. So the problem with that is now you have much lower degree of multiplexing, right? So if you look at aggregate behavior of those small populations, it's not as stable as if you have a large population, right? So simply to get all of large numbers is not going to be as effective. When we talk about 1 million users, you can look at the aggregate behavior. Okay, so this is why traditional caching algorithms is not going to work well, right? So we're talking about least frequently used or least recently used caching algorithms. Those are the simple ones, but effective when we talk about centralized caching. But now for edge caching, most likely they are not work well. So this is why we want to have some kind of a better or new edge caching algorithms. This is actually really a motivation for our work. Okay. So the idea is, again, the rule of thumb here is that if you want to achieve, let's say, higher caching performance, you want to achieve higher, let's say, content hit ratio, you place contents that are most likely to be requested in near future in your limited space, right? So that's basically the idea. Okay. But the challenge here is how can you predict which content will become popular, right? So what are those content will most likely be requested users in a short future time window? Okay? So that's a key problem for caching. Okay. So there are some kind of a simple or statistic-based predictions, right? So for example, when I talk about LRU, you really look at those algorithms. They are very simple prediction, right? Let's look at, for example, LRFU. Basically use the content popularity in the past time window before now as prediction, right? Because there they said, the content get requested least number of times will be kick out from the cache, right? Because not likely going to be requested in the near future, right? So very simple statistic-based prediction, okay? Error are same. So they are using a different heuristics. The basically says the content requested more recently will be more likely to be requested next, right? The least recently used will be kept in the cache, okay? So as I said, those simple statistics-based predictions work okay. You have a large population, but if you have small populations, since the kind of the content request popularity is not going to be as stable, so most likely they're not going to work well, okay? So our goal here is we want to dig deeper into the kind of content consumption history, and we try to obtain more fine-grained and more accurate user content interest predictions, right? That's our kind of main goal of this work. Okay. So hopefully I have enough motivation and a rough idea how we're going to go about solve this problem. So now I'm going to tell you a little bit more detail about our approach. So the critical thing here for us is to predict user or group content interest, right? So it turns out, and we can borrow some techniques from some different area. This area is called a recommender system, and in this area actually study predict user interest, right? So the basic says that we are living in this kind of a digital world. We have this kind of information overload problem. We have too many choices, right? So those recommender system help us to make a choice. So this area is actually rooted back to cognitive science, information retrieval, but has become kind of independent research area since the mid-1990s, right? Because there are lots of kind of real applications. So nowadays, when you go to Amazon, when you watch movies from Netflix, when you listen to music from Spotify, they all give you some kind of recommendation, right? Which means they look at user content consumption history and they're trying to predict what you want to watch or what you want to listen to next. Okay. So there are two kind of mainstream approaches. The first direction is what we call the user-based, sometimes called a collaborative filtering-based recommender system. So the idea is trying to recommend items to users liked by some users with similar tastes, right? Okay. So then the key question here is how to identify similar users. Okay. Then you say I can look at the user profiles and using online social networks. I want to find out whatever your friends like and I will recommend those items to you. Or I can look at the content consumption or rating history of all the users, trying to find the similarity between users. Okay. Another kind of stream is called a content-based recommendation. So in this case, I know what you have consumed before, then I'm going to recommend some items similar to those items, right, to you consumed before. Okay. Of course, now key here is how you can find similar items. You can do content analysis, right? So if you have the text-based, let's say, content, so lots of techniques you can do that. Or you can have some kind of description of the items, you can compare that. And also you can do kind of looking at the rating history. So let's say, what are those items have similar ratings as this item, right? So you can, based on those information, you can do a content-based recommendation. So for this talk, we're going to focus on user-based parts because our assumption is the CN operators does not have access. That's it for now, for this item description. Okay, I only know the user content consumption history. That makes sense, right? Because at the end, know which user access which content, right? So we can use those information to help predict. So one classical technique for this CF-based RS is called matrix factorization. So there's a paper from NIPS back in years back. Basic idea is if you have a user item rating matrix, right, so you know which users, which item that was scored, and now you want to, you notice that this matrix most likely going to be sparse, right? So you're not going to get a whole lot of ratings. So now, given all the observed ratings, you want to predict the let's say, observed ratings, right? So if you can predict those, missing ratings, in a way, you're predicting how likely the user is going to consume something, right? So this essentially becomes a matrix completion problem, okay? So this approach is actually what we call the probabilistic generative model. So assume that user interest can be modeled by latent factor. Okay. So likewise, the content also have a latent feature. Okay. So based on this two kind of a latent content and user latent feature, so you can predict. So what is the user's rating for each item? Okay. So now we can use this probabilistic model, and you can use in the observed rating to the training, right? So after training, you try to identify the user latent feature vector, and you try to identify the content latent feature vector. Okay. So after you have those two vectors, you can predict ratings, right? Right. So initially, how are we going to map this to our problem? Remember, we are trying to solve the caching problem. Okay. So here we are assuming that we have this kind of a caching network. So we first have some kind of distributed edge caching servers. Right? So they handle small user populations, but they are connected in a network, which means so they have multiple, let's say, hierarchy. But now eventually you can talk to some kind of central content distributor. Okay. So in order for us to do this MF-based edge caching, what's going to happen here is so edge server is going to collect the user content access information. Then they're going to forward those content access logs to the central distributor. Okay. So in this case, the edge server is only very light. Okay. So then on the central server side, they are going to collect all the information from all edge servers, right? So then they're going to do this, heavy computation to do user content interest mining, right? So after that, they identify, let's say, they predict the user content interest, and they push this to edge server so that they can use this information to do caching. Okay. So now the challenge here is as a CDN server, let's say CDN operator, we typically don't have this poor user rating for each content, right? Because first of all, they only have the user content access logs. Okay. And also, whatever the CDN sees is not individual user ID. They only see the IP addresses. So which means there may be multiple users behind the same IP, either due to the net issue or maybe multiple users share the same computer. So it's really hard for, say, CDN operator to get a poor user rating history. So this is why we do what we call the group-based MF. So instead of predict the interest for each user, we predict interest of all users behind the same IP group. Okay. So in this case, let's say the rating matrix for each row is a rating for each IP group. Okay. So each IP group can be a subnet, all the users behind the same subnet. And now we also don't have the rating for this content. What we have is a number of requests for each content, right? So we can count how many times each content is requested by users behind the same IP group. Okay, then we do a bit of normalization. We get a kind of a rating, group item rating. Okay, so based on that, we can predict how likely each group going to access some content, right? So using that as a score can help us to do caching. Okay, so now next I'm going to quickly talk about how we're going to do this hybrid edge caching solution. So the first way is we're trying to map this MF-based, let's say, algorithm directly to do caching. But the challenge here is, first of all, we need to collect lots of information from all those edge servers. And also the computation is not easy, right? So for example, when you deal with this rating matrix like 1,000 by, let's say, 100,000, and it takes several minutes to get the results. So which means there is no hope you can update this in real time. So which means you're not going to update this MF result for each request. Okay. So this is why our solution here is run MF with limited frequency. You can set up the frequency, right? So for now, we say just do this once a day. We want to predict user interest once a day. And also for data collection, say we don't want to kind of flood the network. You say I want to only do this data collection when the traffic is light, for example, at midnight, right? So all the kind of cache blocks that exchange those traffic logs. Okay. But now if you do this, it's a problem. It's because you say what about the content request dynamics between two updates, right? Because between those two updates, the cached list generated by MF is not going to be changed. Okay, so which means you're going to miss those dynamics between those two updates. Okay, so this is why we propose a hybrid solution. In this case, we want to combine those more kind of MF or CF-based prediction with real-time active caching algorithm. For example, the traditional LRU or LFU, because they update their cache list for each request. So which means we're trying to get the best out of both worlds here. Okay. So one solution is we can do this what we call the hard combining. So in this case, we let's say we have a cache list generated by MF, right? That's based on the the predicted score. Then LRU also generates the list, right? So then we allocate, say, some portion to MF, and the rest go to LRU. Okay. So end up we have this kind of hybrid caching list, right? So which means some part of the list is not going to be changed during the day, but some part of the list will be updated by each request. Okay. Hopefully by doing that, we can capture the content to request dynamics at different time scales. We also try another kind of hybrid solution is what we call collaborative filtering-based LFU. Okay. So everybody know LFU. So they're looking at they get rid of content with fewest requests, but they only look at what happened within the same, let's say, under the same cache. Okay. So obviously we say that's not enough, right? Because in order for you to do a prediction, you also need to look at what happens in some other groups, some other subnets. Okay. So in this case, we actually use another low-cost CF approach called K-nearest labor. So in this case, we first try to measure the similarity in groups, looking at their content request history, right? So the simple thing you can do is you can look at for each group, right? So you have a little content, and for each content you have a number of requests over some history, right? So then you have two vectors, one vector for each group, then you can calculate the similarity between those two vectors, right? So use that to measure the content similarity, the group similarity. Then you can identify for each target group, you can identify the K most similar groups, right? This can be done offline, right? Again, you can update, once a day, once every 4 hours, whatever, right? So this is, identify similar groups. Then you can do this what we call KM-based LFU. So in this case, for the content C cached by group I, and you want to calculate its access score using the content request counts, not only from group I, also from, let's say, groups similar to I. Let's say you use top K groups. So you can calculate some kind of content access score. You can use this score to make a caching decision, right? So whether you want to get rid of content with a score, and this score can be updated online. Right? So which means whenever you have some requests come in, you can update the score, right? So if you don't want to do this update for each new request, you can do this update for a new batch of requests. Right? Again, you can control batch size, how fast you want to do this. Okay. So those are kind of main two main approaches we proposed in the paper. Then I'll just quickly tell you about 1 minute trace-driven evaluation. So in this case, we use kind of VOD access trace from one major OTT provider from China. So we have all kinds of movie, TV, or news traces. And we don't have the kind of a topology information. And so what we do here is we group IPs by their prefix, right? Again, that may not be accurate, but that's the best we can do. Okay. And also we assume that all the users in the same subnet is served by some edge CDN. By controlling the prefix length, we can control the how deep you want to push the CDN server close to users. Okay. So we compare our methods with two major baseline methods. The first one is LRU, and we also did actually LFU, but the performance is much worse. So I'm not going to include the results here. I only look at LRU, and another called the optimal replacement. So it's not realistic; it's just upper bound. So in this case, you say if you know the future request sequence, right? So whenever you do this kind of replacement, you're going to kick out the content that will be request arrival time is farther away, right? Farthest away. It's called FIF. This is not realistic. You cannot do this in practice, but we just want to get a sense of the upper bound. Okay. So I quickly show you some kind of, try to verify indeed we have this kind of edge caching problem. And the upper graph showing the, content popularity difference between the global popularity and the local popularity, right? So as you increase prefix length, right, which means the popularity in the local network is actually quite different from the global popularity, right? So if you want to use global popularity caching, you may not get good results, okay? So the lower graph here showing you the LRU performance at different group size. So now measure group size by lateral request, right, from this group. As you can see, the performance gets better if the group size is large, right? So it's actually agree with our kind of initial equation. But if the group is really small, the performance is much worse, okay? So then we compare our two main methods with LRU and the upper bound. So you can say, our methods outperform LRU in all groups and all cache sizes. So here we try prefix 16, prefix 18, prefix 20. For each prefix, we try different cache sizes, right? So you can say there's a big gap between LRU and the upper bound, and our approach is actually always better than the LRU approach. Okay. Another interesting here is if we compare, let's say we propose MF and the KN-based approach, and those are the kind of better ones marked by the best circles. Okay. So the basic idea here is that when the cache size is large, I'm talking about relative to group size, so MF actually outperforms KN, right? So the reason is that the KN can capture dynamic hot content, so which means it's the most effective when cache size is small, but the MF can better predict those kind of what we call warm content, right? So when the cache size is large, so this is how the content will be effective. So finally, MF can beat the optimal upper bound. You say why? It's because MF is proactive, right? So which means we can preload content, but FIF is reactive, right? So you can only rebase content based on what's coming. So if your size is really big here, so MF can actually outperform FIF. So I'm going to maybe quickly skip those additional notes here. I'm just jump to the conclusion. So in this work, we basically says that if you can mine the group user interest well, and you can actually significantly improve edge caching performance, which is much needed in a kind of edge caching kind of setting. And we propose this kind of hybrid solution by combining collaborative filter-based prediction with traditional reactive caching scheme. And so that we can capture content request dynamics at different time scales, and also we can control the communication and the computation overhead. Okay. As for future directions, and here we are doing very simple combining. Right? We just do this kind of proportion-based combining, more adaptive combining, and the parameter tuning for different group size, different cache size can be another interesting problem to look at. We also look at, so far we only look at what happens on single cache box. So currently we have some results also say how we're going to apply this to hierarchical caching. Right? So we can do this not only for one cache box, we can do this for multiple cache boxes together, try to do a coordination among them. Then we can say you have more kind of a user data, you can have more content data, then you can maybe do better. Or you can try more advanced RS methods, maybe DNN, if students like to do it. So we're open to that. So finally, come to my talk. Thank you. Time for just one question.
Like this, where instead of using your LRU to generate, we separated out the cache and kept a portion for LRU, and we thought that it might be better to have that separation of having your recommender driving your pre-placement, but having a LRU portion to, base the replacement within that segment. Is that separation useful, you think, or is it better to do it the way you have it here?
Well, I think, the combining here is very that may be more adaptive. With that, I think this kind of hard combining is not flexible enough, right? Right, so I think LRU is very effective to capture those kind of content suddenly get very popular, right? But since we cannot do MF very frequently, which means we definitely need to have like this kind of right, yeah. Okay.
Thank you, and we'll be reconvening in about 10 minutes. I'm sorry that our break is reduced, but please come back and we'll start again.